Welcome to Rational Science. And I want to make sure that you can all hear me because I replaced my sound from my camera, which gives me this echo, and I replaced it with the internal mic from the computer. So first things, please let me know if you can't hear me or if the sound comes out weird or whatever. I still have a little bit of a cold. I haven't gotten over that, throat, coughing, etc. So maybe I need another week, another month, who knows. Okay, we're going to be talking today about fields and the fact that fields, okay, thank you. Fields, it's incorporated into general relativity. The question is that it's, especially the gravitational field, is not incorporated into quantum mechanics. That's where the problem is. And so what the mathematicians over the years figured out is that if they want to have a grand unified theory or a theory of everything, they're going to have to reconcile quantum mechanics with general relativity. And the only way to do that was, that's the one that came to their minds, was through the field. Okay, and so that's where they stand. That's why QFT, quantum field theory, was invented. Okay, and that's what we're going to go over today. Before that, I'm going to get into another touchy subject. It's called mass. Okay, and we're going to find out that mass, the problem is with math, not with mass. We don't need math to solve mass. We need definitions. That's essentially the issue. So what happened? A fellow sent me a link to a book. He says, look, you should read this book about mass. Okay, see what they have to say. But, I didn't get my hopes up because no one has defined mass in the last 400 years. And that's one issue. The other issue is that, even to this day, they have no definitions. They have no idea what mass is. But every mathematician on Earth uses this word mass. Same with time, by the way. So they don't know what mass is, but everybody uses it. And so that's where the problem is. And so this is the book that this fellow suggested, okay? And it's from this fellow called by the name of Max Jammer, okay? And he says, Concepts of Mass, okay? So instead of going out there and buying a worthless book, I just went to see the summary. And I'm glad I didn't buy this book, and I don't think I would recommend it to you either, because the issue, again, is definitions, okay? And so here you see just a couple lines that I underlined there. Persistent difficulties of defining inertial mass, okay? So they don't know what inertial mass is, let alone mass, right? Then whether mass is an observation or a theoretical concept, okay? And so now we have the issue of whether this is an issue of experiment, observational, or whether you stay at your desk, drink a beer, and just think about, the theory, the concept. And again, the question with theory is that theory is not the same thing as definition. Okay, so we have a third one there that's missing, which is the definition itself. Okay, so you have observational, which is what mathematicians do, theoretical, which they don't do, and definitions, which they obviously never did. Okay, they never defined the word. They have these different notions. And then this fellow goes over the problem of whether the relativistic rest mass is the only legitimate notion of mass and whether it's identical to Newtonian mass. And obviously it ain't. There's a difference between Newtonian mass, which is quantity of matter, and that's the notion he had, and the notion of mass that came out of relativity. Okay, there you have at the bottom. Jammer then devotes a whole chapter, okay, to the distinction between inertial and gravitational mass. Yeah, if he doesn't know what mass is, much less he's going to know what the difference is between inertial and gravitational. And then he moves on to try to figure out the equivalence principle, the principle of equivalence that Einstein allegedly discovered, that gravitational mass is equal or very close to equal to inertial mass. And yeah, they're exactly the same, but these people go out and do measurements instead of thinking. And they don't understand what gravity is. They don't understand what mass is. And that's why they go out and measure and try to get operational definitions. And then he concludes his book by trying to figure out the origin and nature of mass. No, he should have started the book with origin and nature of mass. We need to know what the nature of mass is before you go through all of this other nonsense. And obviously, he ends up his book without understanding anything about mass. And so why would you buy this book? What would be the purpose of buying a book where an ignoramus is trying to educate the public? Person who doesn't know what mass is, never defined it, is trying to figure out the differences between inertial and gravitational mass. When he doesn't know what even mass is, how can he understand the difference between one and the other? And then, again, he's going to end up his book the same way everybody ends up today. I don't think he discovered anything new, where they say, look, apparently gravitational mass is very, very close, almost identical to inertial mass. We don't know why, but, they're about the same. And again, the difference between them have to do with the equations. You have inertial mass is equal force equal to mass times acceleration, which is Newton's second force law. Okay, and that's when you push something or pull on it, right, more or less. And then on the other hand, you have gravitational mass, which is Newton's gravitational formula, which is gravitational constant G, mass divided by distance squared. And so the question is, why would this gravitational equation be equal to the inertial equation? If you're running out of the earth, right, and elevators pushing you up like Einstein imagined, and you're falling towards earth, why would those be the same at a given point? Why would they have to be equal? They're two different mechanisms. And so this was the starting point for all this stuff. Okay, so another issue related to mass, which had to do with some of the subject matter I covered the other day, and it's got to do with this. I went to the bot, AI, and our little R2D2 to try to figure out, what R2D2 has to say about, mass and space-time. And the question was whether space-time required mass. And so the answer from the bot, which is obviously programmed by the mathematicians, right? So this is a collective knowledge of mathematical physics, right? No, space-time is not irrelevant without mass. Even in the absence of mass, space-time still has properties and is a fundamental part of our physical universe. The key aspects of space-time that exist independently of the presence of mass are, and he goes and lists three at least. He says geometry, right? You remember gravity is the curvature of space-time. But there is no geometry to space-time unless there's mass there, because it's the mass that produces the curvature. These people say that you can do without mass because you have curvature. In other words, it has the property of curvature. And it doesn't have property of curvature unless you put a mass in there. So space-time does not have an independent curvature of its own. Then light propagation says that, light travels at the same speed through the vacuum, whatever the vacuum is, because they say the vacuum is full of stuff. But anyway, it says that light travels at 300,000 kilometers per second. But see, light is a particle. It's a little ball known as a photon. And so we have a problem with that because they said the condition here is that, we wipe out all matter, all particles from the universe, including the particles of light. We have no idea under these assumptions whether particles are necessary, like atoms are necessary in order for there to be light, because it's the atoms that create light according to quantum mechanics, right? They emit these light particles, photons that come out of the atom. And so we don't know if light propagation remains the same once you remove all matter from the universe, including the so-called particles of light. Okay, so again, they have all these contradictions. They can't think these things very deeply. Okay, then the issue we are going to cover today, the quantum fields, right? It says even though space-time is there, you have the electromagnetic fields inside it, whatever a field is. But then it turns out that all excitations of field, according to the what we're going to cover today and what been the catechism out there, an excitation of a field turns into a particle. That's what a particle is, an excitation of a field. So, how can you have a field without a particle if the fields are always vibrating and particle is a vibration of a field? So again, all these contradictions that these people, these these irrationalities these people live with, and they just move on. They don't even bother to analyze what they said. And space-time, according to Einstein, was just an underlying framework that exists independently and has all these properties. He even said that space-time is an ether, or general relativity cannot live without the ether. Why? Because space-time itself has properties independent of matter. Okay? So we talked about that last week, and no, right now they can't show us that there are properties, and Einstein said, look, my ether is a little different than the 19th century ether. It's still an ether, but it's a little different ether. And he says you cannot really fix the ether and gauge your distances with respect to this fixed ether. The ether also moves, right? And so you're pegging your reference to something that is already in motion. And so he had this dynamic ether, which was different than the one from proposed by Lorentz, for example, right? So Lorentz had this more or less static ether, and Einstein said, no, mine is moving. But they all talked about the ether. And we haven't gotten rid of the ether even today because, as we will see, the ether has only changed as far as the properties that they assign to the ether. And again, they don't call it ether. Why? Because it's taboo. Okay, and so here we have the origin of the problem of mass, and that is that no one has a definition of the word mass. Nobody has an idea what they're talking about when they use the word mass, like nobody knows what they mean when they say God exists or God doesn't exist, because they never defined the word exist. So nobody knows what they're saying when they say God exists or this chair exists or doesn't exist. This is the problem, definitions. Okay, and here we have the definitions from the Wikipedia. Says there's at least 7 different aspects of mass. Okay, 7 physical notions that involve the concept of mass. And there you see a few of them. And one of the problems, they try to define it operationally. And operational and functional definitions are irrational. The person is saying, look, let me run an experiment and tell you what mass is. No, that's not the way it works in science. The way it works in science, you design your experiment beforehand. And you submit it to your bosses so that they approve it. And if it's irrational, they don't approve it. That's how it works, at least in engineering. And so these people are introducing mass, and they're saying, let me run an experiment. And at the end of the experiment, I'm going to tell you what mass was throughout my dissertation. And that's not the way it works. So an operational or functional definition is an irrational definition. And there you see, you have different notions of what mass is. You have one, which is a notion of resistance. Okay, the other one is the notion of weight. It says active gravitational mass is a measure of what? Of the strength of an object's gravitational flux. How an object reacts to gravitational field. And that's called weight. Very simple. So this mass is equal to weight, and they never say that mass is equal to weight. They say, no, mass and weight are 2 different things. No, there it shows that weight and mass are exactly the same thing. And then you have the notion of mass that Newton had, which is the quantity of matter. When they talk about rest energy or rest mass, they're talking about the number of particles that comprise that object. That's the quantity of matter notion of mass. And so you have all these different notions, and of course they can't make sense of anything that they talk about because they have all these contradictions that they never resolve. You cannot, run a discipline such as physics with 10 different types of mass. We need to know what mass is and just stick to it. And if you got some other notion out there, call it something different. But see, what they did was they took Newton's mass, and over the years they changed it a little bit, gave it different properties, different notions, and that's how they ended up with 7 different types of mass. No, mass is quantity of matter, and only then you can say, well, it's different than conceptually than weight. You take the French kilo that used to be the standard for mass. You take it to the moon, it has a different weight. So you say, well, something changed. On Earth, the weight was such and such, and the moon is, I guess a sixth plus. Okay, fine. So the weight changed, but the object remained the same. You didn't whittle out any atoms from your standard when you took it out there. And so if you're going to refer to mass as the quantity of matter and weight as the difference in gravitational attraction, then you can make more or less sense of this. But again, nobody counts atoms when they give you mass. They give it to you in kilograms, which is a measure, not a counting. Measuring and counting are two different things. If you count atoms, that's one thing. If you measure something like weight, kilograms, that's different. And so how are you going to determine mass? Are you going to do it through counting atoms, or are you going to do it through weighing on a scale? And what they say, look, the mass changed. No, the mass, the weight changed, right? Yeah, okay, the weight changed, but the mass did not. Yeah, the mass did change also, because the way you determine mass is through weight, by weighing it on a scale and giving it in terms of kilograms. The other one's given in terms of newtons, but irrelevant. They're just measures. No one counts atoms when they give you mass. That's the problem. So again, they don't have a definition, and they use all these 7 definitions sometimes simultaneously, and they don't even realize it. They call it all mass. All of them are mass, right? Okay, and so here's a little bit of an analysis on that, okay? And you've heard of Einstein's famous E equals mc squared equation, right? And we have a problem here, because if mass is the quantity of matter, how can you relate that to velocity or speed? Okay, because see, in that E equals mc squared, the little c there, that's velocity of light squared. And velocity is, it's distance traveled divided by time, which you see there in the second equation. So you are involving motion and time. And the question is whether mass requires motion and time. Certainly not the quantity of matter. It's got 100 atoms. That's it. That's what that stone has, 100 atoms. That's the mass of that stone. And so what's that got to do with distance traveled or time? See, this is the issue. They turned mass into a dynamic concept, which the quantity of matter really is not. And then you have the inertial mass, which is Newton's second equation, second equation of motion. Force equals mass times acceleration. And again, you have distance traveled. That's what that equation says. That if you rearrange the things, put force over acceleration, that acceleration involves motion, obviously. And so again, mass is equal to some kind of acceleration, some kind of motion. And then the question is whether that's the case. Should be the case. Obviously, it wasn't the case when Newton talked about, the distance between two objects. And that takes us to gravitational mass there. The distance there in the denominator, distance squared there, that distance is not distance traveled. It involves no motion and no time. That's just separation between two masses. You got mass 1, mass 2, and they're separated by a certain amount. That we don't care about the number. Mother Nature doesn't, never went to school. She doesn't know anything about mass. All she knows is that there's so much separation, and because there's so much separation, you have a different weight. That force there would be weight, right? So you have a different weight of one object with respect to the other because the separation is different. And we don't need to know anything about numbers in order to conceptualize this. Okay, all we need to know is that, there's so much separation. The more separation, the less weight, and the closer or the less separation that you have, the more weight you have. And that's all there's to it. You don't need to know anything about math to understand the gravitational formula. And again, weight is not a force. Weight is a static concept. There's nothing moving with weight. Weight, you stand on the scale, but until the scale completely stops, you don't have weight. You can jump on the scale and you'll see that it changes its values. And as long as it's moving, you don't have weight. You have many weights. Weight is a single value, and that's when the scale stops moving and you stop moving. And again, if you get 1 inch closer to the Earth as an astronaut, you weigh more instantaneously. Now, it doesn't take the speed of light like the mathematicians say. You take 1 inch, you get 1 inch closer to the Earth, you automatically have a different weight. Because weight is a tension. Okay, and tension is not a force. Okay, but in mathematics it is. In science, tension, it's a tug of war between two objects, and no one wins that tug of war. If one wins the tug of war, then you have force. But as long as no one wins the tug of war, you have tension, and tension is not a force. And again, weight is only valid for a single location, single separation. That's in a nutshell. But let's go further. I'm going to do a little thought experiment here, okay? And we're going to put the Earth here. You see the Earth, okay? And what we're going to do, we're going to put an elephant on top of the Earth, okay? The elephant is falling, I guess, from outer space somewhere, from E.T. who sent the poor elephant downwards to Earth, okay? Maybe the elephant itself is an ET, right? A Martian of some kind. Okay, now we're going to look at a single atom of the elephant. Now, I made the atom very big there so that you can see it, that red mark in the center, right up the elephant. Okay, and we're just going to look at one atom of the elephant. So it wouldn't matter if it's an elephant or a feather, right? What we're saying, there's a single atom. We're only going to analyze that single atom. Okay, what happens? Under the rope model, you have this situation where that atom is connected to every atom on Earth. And no, I did not draw all the connections. Okay, there's gazillions of them because there's gazillions of atoms on Earth, right? So I just drew a few lines to indicate the concept. All the atoms on Earth are connected to that atom that belonged to the elephant. That's what I'm showing there. Okay, and so the question here is, the equivalence principle. How do we know that elephant is leaving the Earth? How do we know that elephant is falling to Earth? Okay, is the elephant in some kind of elevator that's taking him to Mars, or is the elephant in free fall falling on Earth? And that's one of the questions Einstein asked himself, and that's what led him to try to figure out the principle of equivalence. And here it is. Okay, the principle of equivalence is very simple. It doesn't matter if you're going outwards or you're coming downwards towards the Earth. Okay, going outwards, you got force equals mass times acceleration, and coming towards Earth, you've got the gravitational formula. Force equals the gravitational constant g, mass 1, mass 2, divided by distance squared. Mass 1 could be the Earth, mass 2 could be the elephant, and the distance between the elephant and really the center of mass of the Earth, that would be that distance squared, okay, that distance. Okay, and so what's the issue here? The issue is that if the elephant is leaving, or the elephant is coming, or better yet, the atom is leaving or coming towards Earth, it doesn't really matter. At that location, at that distance from the center of the Earth, from the center of mass, right, that atom has a certain number of ropes connected to it, electromagnetic ropes. Okay, so there's only a certain number that are connected to that point. So at that point, inertial mass is equal to gravitational mass. It doesn't matter if it's going outwards or coming towards the Earth. Okay, that's the issue. There's a certain number of ropes, and that's why inertial mass is equal to gravitational mass. And if the elephant is farther out, same thing. It doesn't matter where the atom is. There's a certain number of ropes connected to that atom at that distance. If we freeze the image and we stop all motion in the universe, right? There's a certain number of ropes at that point, and that explains to you why inertial mass is equal to gravitational mass. It's just that simple under the rope model. We don't have to go out there and measure anything. We don't have to go and try to get operational or functional definitions. It's straightforward. Certain number of ropes at a certain distance. Period. We're done. Okay, that's how simple it is. It's simple, very baby stuff. Okay, but the mathematicians are still struggling with it since the days of the Greeks, after 2,500 years. Okay, and here we see it in the Universal movie. What's the Universal movie? Well, the Universal movie is, in a single frame of the film, you have every atom in the universe, no matter where it's at. So all atoms in the universe are in a single frame. We take a snapshot of that, and nothing is moving within the single frame. Okay, so we have all these concepts which are static concepts which fit within a single frame where nothing is moving. You want to see something moving, you need to see more than one frame. But if you see a single frame of the universal movie, 3D movie, right, you have these concepts which are static concepts: object, distance, location, and existence. And within that we have weight. Weight is a static concept. So is mass, if mass is quantity of matter. You know, a rock has 100 atoms. That's what the rock is at that moment in time. Well, that's what it has, 100 atoms. Nothing changes. Okay, you don't have to count them in many frames. That's what Mother Nature recognizes, that rock has 100 atoms. That's how simple it is. But if you're going to talk about mass as resistance, relativistic mass, energy mass, you know, the E equals mc squared, or gravitational, any other mass that you can come up with, you know, then you're talking about, you know, many frames of the film. You're talking about a dynamic concept. So mass is either a static concept or a dynamic one. And they're still trying to reconcile those two. And of course, they never will. It's impossible, because they have a contradiction. They have a contradiction. On one hand, they give mass these movement, these dynamic properties, and in the other case, they want to think of it as, you know, quantity of matter. Like if you take the kilo to, you know, the Lagrange kilo to the moon, well, the mass hasn't changed, but the weight has. Well, if you take it in that sense, yeah, the quantity of matter, that grand kilo, hasn't changed. And that would be the mass of the grand kilo, whatever that is. But then you would have to give the amount in terms of quantity of atoms. For example, you can say that the hydrogen atom is your unit of mass. Fine, if it's the unit of mass, now you say, look, this stone, whatever, that you took to the moon has exactly 1 trillion atoms, meaning hydrogen atoms. So that's the mass of that stone. But you cannot say it's so many kilos or grams or pounds or whatever, or tons, right? You can't use weight, you can't use a measure. It's got to be a counting, not a measure, something that you counted, okay, or whatever number of atoms it has, okay? And that's different than measuring something. And what these people do, they don't understand the difference between counting and measuring. And that's another problem that the mathematicians have. Okay, and so with that we get to the black hole, which is what they all are studying today, this big massive object that causes so much gravity, etc., etc. And here we have one university, and this is what they put in their physics site of this university. It says, relativity showed that gravity is related to the curvature of space. Okay, so now we're talking about curvature of space. We're not talking about, you know, how many atoms something has and that causes gravity. Now we're talking about curvature of space, right? No gravitons flowing. We're saying it's just bending of this thing they call space. And that a black hole is a place. I like that. It's either a curvature of space or it's a place, okay? Where the curvature becomes so extreme that a hole forms, okay? And it says a mass distorts or bends space. Okay, so that's your gravity there, right? To form a black hole, a lot of matter is needed, but must be concentrated in a small amount of space. Matter continues to collapse to a point that is known as what? A singularity. There's a big singularity. So we need to come to terms with what this singularity is in order to understand what a black hole is. And for that, you need to know what mass and gravity are as well, right? Because singularity is formed apparently through, you know, gravitation acting on masses. Okay? That's the way the mathematicians see it. This point has infinite mass and density and is infinitely small. They all use all these infinities, infinitesimalies, and etc., right? They talk about infinite infinitesimal. Okay, so this is the problem. The problem is that they don't care these words. When they use infinite and infinitesimal, what they're doing is putting it beyond your reach. That's what they're doing, and so that you can't question it and say, well, it's infinite. Like, you know, go to infinity and find it. You know, see if you can find it over there. So they put it beyond your reach, your capacity to even imagine this thing. And so they like all these infinities, and singularity is just you know, the perfect thing for infinity and infinitesimally, and so on. Anyways, the effect of this point on space-time is to distort It's so that nothing can escape from the immediate region, right? Near singularities, the known laws of physics break down. What do they mean by that? Well, what they mean is that if you get close to the singularity, you get infinities. You never get to stand on the dot, okay, even for a split second, right? Because there is no dot. It's a region where everything is approaching, where all the matter is getting closer and closer to the singularity, but never makes it there, okay? This is the notion they have of a singularity. Here, let me illustrate it for you. You're always reaching that center, but you never get there. Matter just gets closer and closer together to each other, but it never reaches, the end of the tunnel. There is no end of the tunnel. It's just infinity. And the problem with this is when they apply it to Big Bang. They say, look, the Big Bang singularity. So all the matter in the universe, all the galaxies, all the stars, everything's falling into the singularity. But what are they saying? They're saying it never reaches there because there is no there. Okay? It just gets closer and closer and closer forever. But then this destroys the notion that Big Bang started 14 billion years ago. It can't be because if you go back in time, you won't find an origin to the singularity, because singularity is not a thing. It's just a region where everything's falling in like a drain, but it never gets there. It never gets into the hole. It's just approaching, getting ever closer, forever. And so this is a problem, that these people have, that they don't define these things very well. And they do it more or less on purpose so that you don't ask any more questions. And they said when matter falls into or comes closer than the event horizon of a black hole, it becomes isolated from the rest of space-time and can never leave that region. For all practical purposes, the matter has disappeared, from the universe. So if it disappeared from the universe, where in the world did it go? I mean, the universe is everything, right? So if the universe is everything, how can you disappear from everything? Where do you go? Into nothing, I guess? I don't know. So they make these statements and they don't even know what they're saying. They never analyze what they're saying. It says once inside the black hole's event horizon, matter will be torn apart, right? Break it into pieces, okay? Into its smallest subatomic component and eventually be squeezed into the singularity, which again is not a thing. It's a place where things are falling in, but they never fall in because they never reach the singularity. It's, they're forever traveling towards the singularity and never reach there. There's no train station called the singularity. Okay, you're just approaching it, always approaching it, never getting there. As the singularity accumulates more and more matter, the size of the black hole's event horizon increases proportionally. Well, I don't know how I can increase proportionally because, again, how can you be approaching the singularity and never getting there? And so are we saying that the matter is still inside the black hole between the event horizon and the singularity? That matter is forever falling in, but it's always there. It's always close to the singularity of the black hole. So then, the matter is still there. It gets crushed. It gets broken up into crumbs. You don't have a bread. You have crumbs. Okay, so you have all these crumbs, but the crumbs never disappear really because they're always approaching the singularity. This region, this space, this location, position, place, whatever you want to call it, it's approaching this region, but it never gets there. And so where is this matter? It wasn't completely crushed out of existence because it never made it to the singularity, whatever that is, and it did cross the event horizon, so all this matter should be scattered all around somewhere between the event horizon and singularity. And so, again, it's all misconceived. None of it makes any sense. And the only thing they can tell you is the laws of physics break down at the singularity, whatever that means. What they do is just put it beyond your reach. Okay, so what is mass? What is gravity? What is this singularity? What is all this stuff? They asked Neil Tyson, right? Good old Neil Tyson. They asked him, what is gravity? And here's his answer, okay? And I guess you can fit that in with singularity and with mass as well. And here it is. This is what good old Neil said, okay? He said the following. Give me a second here. There he goes.
We can describe gravity. We can say what it does to other things. We can measure it, predict with it. But when you start asking Like what it is, I don't know. I don't know. I don't know. I don't know. What it is, I don't know.
So, should we ask Neil, if he can answer the question, what is gravity, Neil? And he says he doesn't know. You don't know what gravity is? I thought everybody knew what gravity is. You don't know, Neil? Come on. He went to school for 10 years. He doesn't know what gravity is. And here, let's see if we can enlighten him. This is what he should have answered. Okay? Give me a second here. Went through the other side. This is what he should have answered. There he goes. That's what he should have answered. He should have said, look, under general relativity, right? Give me a second here. Under general relativity, gravity is warped number lines. That's what it is. Nothing has changed in the last 100 years since Einstein, came up with general relativity, his field equations. He said it's the warping of space-time, meaning warped number lines, because space-time is just a bunch of number lines, 4 number lines, okay? And he illustrates as a fishnet, okay, great, okay, I don't care. You can't illustrate concepts with objects like he did there, but that's what they say gravity is. It's the warped number lines. And so that's what he, Neil Tyson should have answered. Neil Tyson says he doesn't know what it is. What did he study 10 years at the university for? I think. Maybe just wanted to see. Okay, let's get to the subject matter of today. And we talked the other day about ether. We've been talking about the ether. We talked specifically about Einstein's ether. And this was Einstein's ether. Here it is. Okay. And this is more or less what it looked like. He was thinking a bunch of particles. He was saying that it moves so that you can't gauge your certain things, certain phenomena with respect to this dynamic ether, okay? And it's a very different ether than the one that Newton had. This is Newton's ether. Boy, it looks exactly the same if you ask me, but, they say it's a different ether than the one Newton had. And apparently it's very different, these two ethers, than the one that the Greeks had, which was this one, which again seems like exactly the same ether. Looks like they all had the same ether if you ask me. But in the case of Aristotle and Plato, they had this notion that the ether was really outside the earth. It wasn't here together with us, with the air and with all the stuff here on earth. No, it was outside the 4 other elements that comprised the world in which we live. That's the notion that Aristotle had. So the ether really hasn't changed at all as far as what it is. It's always been a bunch of particles. That's all the ether has been. What they've done in the 19th century, especially in order to explain light, is they started giving it different properties. It turns out a lot of those properties had already been discussed by the Greeks. They already had discussed, whether there's any motion of the ether, because they said, look, whenever something moves, it has to move into an empty space, but there is no such thing as empty space. What has happened is something moved out of that space and something else moved into that space. So they had all these notions, and they rehashed these same notions in the 19th century in different ways. They had the earth dragging the ether around, called ether dragging, and they had the static ether, they had the dynamic ether, they had all these ethers, but no one said, look, this is the ether, and point to it, like you would point to a rock, right? So nobody pointed, everybody just said, well, you understand what I mean by ether. Yeah, I guess I do. And they all meant the same thing, bunch of particles. Whenever they talked about the oscillation of, light, the fact that light was some kind of wave, it was the waving of the ether. That's what they imagined. And what was the ether? A bunch of particles. It had to be flexible, then it had to be also solid to carry waves, and so on down the line. So they had all these kinds of problems. And even to this day, they haven't resolved any of that. They still have the ether. And here we have a fellow Nobel Prize, just so you say that. Don't accuse me of inventing all this stuff. Here's Robert Laughlin, Nobel Prize, and he tells it to you in your face. Says, the modern concept of the vacuum of space confirmed every day by experiment is a relativistic what? Ether. But we don't call it that because it's taboo. Yeah, it's taboo to talk about the ether, so they don't call it that. But that's what it is. It's, general relativity and quantum mechanics have not invented anything new. They always refer to that region they know nothing about as the ether. It's like the world of spirits, right? That's what it is. And this is the way they illustrate that ether, okay? Out there, this is not mine again. This is from all these great geniuses who came up and said, look, that's the ether. I don't want to call it ether. I'm going to call it the false vacuum or whatever. So this is what they have. They have all these virtual particles popping in and out of existence. And when they stop existing, the question is, what kind of hole do they leave behind? Again, I guess the space is filled by an expanding particle. Who knows? They never resolve these issues. They just leave them hanging there and say, look, that's what we think is out there in the region we call empty space or vacuum. It's full of ether. I didn't mean to say ether. I mean to say virtual particles. So yeah, they have these virtual particles, which is another word for the ether. That's all it is. Okay, another term. Okay, and starting at the beginning of the century, the 20th century, you had people like Einstein and Lorentz and Poincaré. All these people came up with these notions and eventually ended up with what we called today quantum mechanics. You had also Niels Bohr and Rutherford and so on, and they all came up with these notions. And what was the notion of quantum? Why is it called quantum? Well, it's called quantum because it's about quantities, about amounts, about values. And so here you had two fellows, two of those most prominent fellows, Max Planck and Einstein. Max Planck, 1900, he comes up with his notion, his theory of black box energy, and Einstein comes 5 years later with his notion of how he explained the photoelectric effect. They both win Nobel Prizes a few years later. Okay, why? Because they proved mathematically or to the mathematical crowd that there's something called the quantity of energy, a packet of energy, an amount of energy, a lump, like a stone made of energy or whatever, however you want to think of it. It's a ball of energy, okay? And so that's what they proved. So that's what the quantum was, okay? So very straightforward. They're talking about little balls. They're talking about this. They're saying, look, quantum is this, a little packet of energy. Think of that not as a ball, but as energy. Maybe it's round, maybe it's cubic, I don't know. But it's a discrete entity. That's my point, okay? And they both proved it. They both won Nobel Prizes for it, so it was a done deal. We're done. Quantum has to do with particles. The Standard Model talks about particles. What is a particle? Again, an encased ball of energy. That's what it is. It's a lump. And that's not what we have today. Today, somehow, it morphed over the years, and they have what is known as quantum field theory. So they went into the field notion, and they call it quantum field. They put the word quantum. They don't want to get rid of the word quantum because that would destroy all of what they did in 100 years. So they leave the word quantum, but they added field. And they said, well, we have the electromagnetic field, we have the gluon field, we have the quark field, we have all these fields, maybe even the graviton field out there, Higgs field for sure, So you have all these fields out there. And since you have all these fields, maybe that's the way to approach, to reconcile, quantum mechanics with general relativity, which is a field theory. Guess what? So, in order to, blend them somehow, get the gut or the toe, grand unified theory or the theory of everything, well, you got to talk about fields and not about particles because space-time or general relativity cares not for particles, okay? Which is not true either because an event is a point in space-time and all these points make up space-time. So again, we're talking about a particle notion of space-time, right? So it's not completely true, but you get, I guess, the notion of what these people are trying to do. Okay, so what happened? Today we have this. We have Sean Carroll. He tells us that, how this morphed from quantum, the quantity, to the field notion. And listen to him, because if I tell you that, you say, well, Bill, you're saying this. No. Here we have a guy out there, a mathematical physicist who's representing his guild, his discipline known as mathematical physics, he tells you that they switched over from particles to fields. Okay, and here it is. Give me a second here and I'll run it for you. There it goes.
Imagine there is a field filling the universe. And what that means mathematically is just that at every point in space there's a number, the value of the field. And this idea of a field turns out to be quite useful. And that's what we do these days. We talk both about particles and about fields. So particles and fields are the two things that physicists talk about when we talk about the ingredients that make up reality. In one sense, a particle and a field are the opposite of each other, right? A particle is something that is one location. Here's the particle, it's nowhere else. A field is the opposite of that. A field is everywhere. At every point in space, there is a value of the field.
So what is a field? Well, it's a value at each point in space. And this so-called field, these numbers, I guess, they extend to infinity, meaning to nowhere so that you don't ask the question. Okay, that's how far it extends, forever. And so with that, they fixed the problem. You don't ask questions about where the field ends, but it is an extended entity. That's how they visualize it. And then, so what is a particle then? Where did particles go? The quantum particles, standard model, what happened to that? And he tells you here, that a field, that a particle is a field excitation. Again, good old Sean Carroll. Let's run them so that you can hear him, right? Not me. Here goes.
Is light, for example, a particle or a wave? A wave is sort of a vibration in a field. So what's the answer to this? This is the answer. It's fields. It's not a mystery. They always tell you that question. They never tell you the answer. You need to stop thinking of the world in terms of particles. You need to start thinking of it in terms of fields. There are particles in the world. No, there aren't. That's the secret that we physicists have never told you, but here I am, I'm going to tell you right now. The world is made of fields, but quantum mechanics says when you look at the world, you don't see it directly. So the reason you think that there are particles is because there are actually all of these fields filling empty space. At every point in space, there's dozens of little vibrating fields in front of you. But quantum mechanics says that when you look at the fields closely enough, they resolve into individual particles. Quantum mechanics says you look at that light very carefully and it turns into individual particles called photons. Photons are the particles that you see when you look at a wave in the electromagnetic field. The reason why light resolves into photons is because quantum mechanics says that when you look at it, that's what you see. The relationship between particles and fields is that fields are what the world is made of, particles are what you see. So the atoms in this table, the electrons, the quarks, the protons, these are all vibrations in fields. There's a quark field that is vibrating. You look at it, you see quarks. There's an electron field that is vibrating. There's a neutrino field that is vibrating. There's a gravitational field that is vibrating, and so on and so on.
Okay, so what you're seeing there is that all these particles are simply vibrations of the field, local vibrations of the field. That's how they fix the problem, okay, conceptually. They're saying, look, the field, this thing that general relativity has, is this extended thing. And how do we fit quantum mechanic particles with that? Well, very simple. All you say is that it's a local vibration of the field, and now you fix the problem. You have the particle and you have the field both in one theory, one notion, right? Basically mathematical notion. Just so you see that I'm not cherry picking anything here. Here we have another fellow. His name is Arvind Ash, and he's another prominent guy who's trying to peddle his stuff on YouTube, right? And this is what he has to say again, that particle is a field, a local vibration of the field. Here it is.
We can visualize these fields as a kind of ocean. Just like the ocean wave has some turbulence, the fields always have a kind of turbulence, even in their ground state of minimal energy. This turbulence is due to the virtual particle creation and annihilation I just described. In these turbulent seas, if there's enough energy, a large wave can be created, which can be measured. These are the real particles. So particle is nothing more than an excitation in this field.
good old Ash. He's saying that the particle is just a vibration of a field. He's saying it's like an ocean, the ocean vibrates. Yeah, but when the ocean vibrates, it doesn't turn into a particle. It doesn't turn into a fish, which is the particle analogy in this case, right? So they're saying here you have the field, but it turns into a particle, a discrete particle. And they never show it as a discrete particle. Notice that it's a peninsula. It's not an island, it's a peninsula coming out of the field, right? And then it goes back to being the field, but it never gets completely isolated. So they never clarify these notions, which are not completely rational, right? They just leave it hanging there and let you figure it out. See if you can visualize it, right? So this is part of the problem that we have today, okay? That, they leave it up to everybody to figure out what they're talking about. Okay, so none of this really is new. You could say, well, they came up with these new concepts. No. Here we have, I showed you the other day, this fellow, and his name was Lord Kelvin, and he was saying the same thing. The ether, the vibration of the ether, different vibrations of the ether were different atoms. They had already discovered that there were different atoms out there. Mendeleev discovered all these categories of different atoms. And so Thomson was trying to make sense of this, and he said, hey, very simple. We have all this ether. They have different vibrations, and because they vibrate differently, they have all these different atoms. And so he pictured it like all these swirls, these spirals, these whatevers. And he said each one of these is a different atom. It's just different manifestations of the ether. Okay, that's how he visualizes things. Okay, and this is the issue. The issue is that these are not new concepts. They're just rehashing the same concepts and doing it all over again. They're taking all these fields now and they're saying, well, the field is out there. They're everywhere. And all these fields, they're superimposed upon each other. You can see that what Arvin Ash did was he put them in parallel. And then he put them communicating with each other by some energy transfer or whatever nonsense. And so they have all these fields, but they have them in parallel. Why in parallel? I thought they were all superimposed upon each other, that every field, whether it's a gluon field, a quark field, a Higgs field, or a gravitational field, they're everywhere in the universe. Each one of those covers the entire universe. And if they cover the entire universe and little blips here are the gluon, the quark, or whatever, how can they be communicating with each other through transfer if they're all occupying the same space? The gluon field is the same thing as the quark field, is the same thing as the graviton field or the Higgs field. They're all in the same place. They're all superimposed upon each other. How can they send anything, to where if they're already there? So they have all these contradictions, and they live with all these contradictions, and they don't care about it. They just do math. They just care about the equations. Anyways, here we have this good old Arvid Ash again, and he says the following, that quantum field theory did not really replace quantum mechanics. It supplemented it. And here it is. Listen to him. You can get started here. Give me a second. Here it goes.
There has been one additional, more recent paradigm-shifting development in physics that perhaps did not receive as much fanfare, but it is undoubtedly equally profound. And that is how quantum mechanics was supplemented and made more complete by quantum field theory, or QFT. It is the basis of the best theory we have in physics today to explain nearly everything, called the Standard Model of Particle Physics. What is quantum field theory? Why is it necessary? How is it different than quantum mechanics?
Yeah, quantum field theory did replace quantum mechanics. Nobody noticed, and like he said, it was kind of subtle. It came in there, and there was a revolution that nobody noticed. Yeah, and nobody noticed that they did change quantum mechanics. Quantum mechanics is no longer a particle theory. Nobody believes in the discrete particles. They went back to the 19th century where they said, look, the ether is everywhere, and it vibrates, and particles are simply the vibration of the ether. These people are saying exactly the same thing almost 150 years later. They're saying, look, what you've got out there is just this world of virtual particles, and they vibrate, and they have all these fields, whatever those are, and they vibrate, and locally they become particles. I mean, what can we say? I hope I'm still connected. I got a message that I was disconnected. I don't know if that's true. Okay. Okay, so final thing here is just want to show you that no, a field is not the same thing as a bunch of particles. And here you can see the difference. Okay, here it is. Quantum discrete particles, which are not even particles, by the way, they're just amounts. Okay, that's very different than what you see on the right, which is what general relativity proposes. And okay, thank you. You can see that the discrete particles are not the same thing as extended fields. And the fields are not fields. What they are is number lines, and particles are not particles. They're actually amounts, values. And so, you have all these notions out there that nobody defines, because if they were to define them, they would have nothing to do with physics. So they leave them as part of mathematics, or mathemagics, if you will. So this is part of the problem. Definition. They don't have definitions for any of these words, anything that you can sink your teeth into, but they're trying to reconcile the ones on the left, the particles, with the ones on the right, the fields. And good luck with that. That's all I can tell them. They're never going to do it. Maybe they're trying to do it mathematically, but then when they have to explain it to the crowds, they say, well, we can't put our equations, our numbers really into words, so we cannot really explain it to you. You need to come into our world of math in order to understand it. But this is the best way we can do it. We say, look, space-time is warped, whatever that means, and particles can be at two places at once. How can that be? Yeah, you got to come into math, and then we'll show you. So this is what's going on and on and on, and it'll never end, because the mathematicians have no clue, or as Richard Feynman says, he had no way of explaining anything to his students. So he says his students don't understand it because he doesn't understand it. And that summarizes quantum mechanics, not to mention general relativity, which again, I think it was in those days, Einstein or someone, Arthur Eddington, one of those, said, there's only 3 people that understand general relativity. And I even have doubts about that. I don't think any of them understood anything. Okay, folks, with that, I'll see you next week, and hopefully my throat will be in better shape.